Alright guys, welcome back. So in the past video I talked about, here's my notes, about the rate of change of the secant line, or the tangent line, sorry, at any given point. And remember when I talked down here about the secant line becoming closer and closer to the tangent line? Well, we're going to see as we zoom into that point really far, we're going to get a secant line that's infinitesimally close to x, where the 2 points that it intersects are infinitesimally close to the point we're looking at. And I can show you a visual so that it clicks more. So here we have a function. X squared plus 1. And I'm using Desmos here so you guys know what it is. And then we look as you look really close at a certain point, let's say that point is x equals 1. X equals 1, when x equals 1, y equals 2. So at the point 1, 2, what is the behavior of this function? And you see, I've drawn a tangent line here, and you can see it only intersects the graph once. But as you get closer and closer, see I'm zooming in, as you get closer and closer and closer and closer to that point, let me not lose the point, right there, you'll find that the two functions, the line and the function itself, intersect, but only at that point. But you can see, as we zoomed in really close, that tangent line and the slope of the tangent line and the slope of the function are pretty much the same. And that's the idea. We're going infinitesimally small. We're zooming in so much that if we take that, let's take away the derivative line here, that if we take the limit of this point right here, we take we zoom in as small as we can go, and the definition of a limit is that it's infinitesimally small, such that if we describe a point or a secant line that connects the graph, say from here and here. Let me put the point on the graph to make it more visible. There we go. So there's our point. So let's say as we get, where's my mouse? From here to here, the secant line that connects those 2 points is much better at getting the slope, or the secant line at those, see, it's still getting, yeah, the secant line at that point, and the secant line touching that point, and at those two connect, it's getting closer and closer to the slope at that point, which you will see is the tangent line. But also, so basically, as you're looking at that so close, I'm going to turn the tangent line back on, and the tangent line, the slope of the tangent line and the slope of the function are essentially the same. So at that point, the slope of the two are the same. And that's going to be important because you're taking the limit of those. I know that my explanation kind of folds on itself, but it's the only way I can think of to explain it. Let me pause for a second. Okay. So let's get back to business. To defeat the Huns. No, I'm just kidding. Okay, so I hope I haven't thoroughly confused you as to what a derivative is and how we find it and why it's important. But you're going to want to know the rate of change of something, of speed on when you're accelerating in a car. let's say you're researching for a car company, and you're trying to figure out exactly how quickly a vehicle accelerates. And you could say, you know, I press on the gas. If you slam the gas pedal to the metal, the car will, it starts out slow, but then it'll get faster and faster. Well, let's say you get, let's say you're testing out an older model car to compare, and you get, it starts out slow, and it kind of slowly gets up. And so that's your graph of speed here. Well, you're going to say, how quickly did I accelerate? Well, here you accelerated much faster, but let's say that you're just planning for a car that hasn't come out yet. You can't take the imaginary, or you can't take the planned car that hasn't been created yet and take it for a test drive. It's just not possible. And it's, even though we're getting good and better at technology, it's not as easy to simulate what a car like that would do. So you're gonna have to predict, based on your other models, what is the difference in the change of these two things. And you say, like, you know, once I hit a certain speed, where does it change, or how much does it change? Let's say when you hit this certain speed, when you start to climb your acceleration more, where is that point? Like, what's going to happen after that? How quickly is it going to go up? And that's an example of when these could be useful in everyday life. Okay, so for every mathematical concept, there's a formula. No, not every concept, but for many concepts, there's a formula. And I'm not going to actually go over the formula quite yet. First of all, I'm just going to go over some notation with you. So you may have seen this f prime of x, or f prime of something. F prime is just another way to say the derivative. So f prime equals the derivative. And you may have also seen something like this, a fancy stylized d over another stylized d, and then x, d over dx. And this is another way to say the derivative. And the way you say that is the derivative with respect to x. And so it's really kind of, it can be kind of like, scary when you first see it, because it's like, what in the world is that? I don't want to do that. That looks like math. That's what I think whenever I see big long math problems. And so anyway, sorry. Now there's other notations that mean the same thing, but they're much less common, and we don't really use them very often. But the most common notation is this one, Lagrange's notation. It's I think he was French. And then this one is referred to as Leibniz, Leibniz, Leibniz. I think it's German. I'm not entirely sure. It could be Swedish or something else. But anyway, Leibniz's notation. And Leibniz is considered as one of the fathers of modern calculus. I think Sir Isaac Newton was also one of the fathers of calculus, and he has his own notation, but I don't remember what it is. And it's less important because it's not used very often. So anyway, it looks really fancy, and we'll explain how this notation came to be and like where it comes from. But first of all, I'm going to talk about the formula. And this is going to scare you, but I'm going to show you the formula, and then I'm going to break it down and show you that it's not so scary as it looks. I'm going to do that in another video.